All right. Hello and welcome, everyone. Good morning, good afternoon, good evening, wherever you are in the world. Thank you so much for being here today. My name is Sarah Alspaugh, and I will be your webinar host coming to you live from Cincinnati, Ohio, here in the US. I'd like to welcome you to today's webinar, our topic, Improving Pipe System Creation with 3D Piping Design and Simulation. And I would like to welcome and introduce our speaker today. With us, we have Chris Murray. I will briefly read from his bio here and then quickly turn things over to him. Chris is the product owner for SimCenter Flowmaster at Siemens Digital Industry Software. For over 20 years, he played a key role in the support and development of SimCenter Flowmaster and has spent the last 5 years working in the product management team. In his current role, he is focused on delivering new solutions for building and analyzing digital twins of piping systems. All right, well, welcome, Chris. We're very excited to have you here today.
Hi, thank you for the introduction. I'm just, as you say, just going to stop my video and then I will share my screen. Okay, so in this presentation, as the title said, we're going to look at how we can improving pipe system creation with 3D piping design and simulation. So first of all, if we start off and look at piping systems, they're basically everywhere. They're in cars, trains, planes, ships, power stations, industrial plants, chemical plants, and also within the machines in those plants in industrial machines. They can be quite small, example being the cooling system in some computers, or they can get very large, like a water distribution system in a city, or the matrix of pipes that will bring oil back from a oil field under the sea. And they can also be quite simple, so a simple pipeline that takes fluid from A to B, or they can be complicated, multi-branched, so fluid coming in and being distributed different places. They can be loops, they can be and various different other configurations. And then they can be used for different things within there. So some fluids you want to move from point to point, oil, say here being an example, or you may be using it to move heat, say for example in the cooling system in your car, to move it from the engine, which is hot, to the radiator, which will cool it and then keep recirculating around. And then within those systems, we can be working with a variety of fluids. We might be dealing with liquids like water, oil, fuel, gases like air or hydrogen, and sometimes we can also be dealing with two-phase fluids. Now, the solution we're going to look at here today primarily deals with incompressible fluids, so that would be liquids or gases that aren't going at high speeds. So when working with fluid systems and piping systems, we need to understand how the fluids and heat flow inside the system, what the behavior is in different operating conditions and different emergency scenarios. So first of all, that enables us to ensure that the system is safe to operate, both for the people operating the plant and for the environment around it, and equally to manage the efficiency of the system so that we can operate it at the lowest cost possible. Now, why is that important for system engineers? So in a world where resources are getting scarcer and environmental awareness is growing, companies are being constantly pushed to reduce their energy and resource consumption. So the US Department of Energy has estimated that the total energy consumption of all the industrial pumps in the USA is about 142,000 gigawatts per year, which is roughly enough electricity to power over 13 million homes. The US Department of Energy also states the effective savings that could be realized during the design phase, where the single component, the entire piping system can be properly sized with a particular focus on pumps. Increasing the efficiency of piping systems is only one aspect that contributes to reduce the costs and increase the profitability. An example in Flow Control magazine highlights that operating and maintenance costs can make up more than 80% of the total lifetime cost of a piping system. So even that small change in the operating cost long term can have a big effect in the design. And finally, whilst efficiency and financial performance of piping systems is important, so is safety. Piping systems can be fantastically complicated and an accident can be fatal. As before, a good design can reduce risk and improve the safety of the system. So to help with this, we've introduced SimCenter Flowmaster for Solid Edge, which is a solution for analyzing flows in piping systems. So we've introduced a streamlined workflow to quickly compute and visualize flow velocity. So the example we can see here, we have a Flowmaster fluid system laid out. We can see here the velocity scale. We can see we've got the highest velocities around the bottom. And we can also visualize variables such as temperature, pressure drop, and the system here would have started from 3D CAD geometry in Solid Edge. The solution does not require simulation expertise to build, and as a result, every design engineer can take advantage of simulation and improve their productivity. So I'm going to just look at this streamlined workflow first. So the first stage is we start in Solid Edge. So we build our assemblies, and then we basically take the piping elements, shell them out, and then from that we can use the workflow to generate this Flowmaster system. So this has been taken directly from here and built into Flowmaster. So there's evidence that basically that can knock about 90% of the time of building these systems up. So I've built over the past 20 years many Flowmaster networks. And the bit that often takes the longest is getting the data from this CAD, measuring, adding component, measuring, adding component. And it's also quite error prone. So by using this automated process to extract the geometry, we can reduce that by up to 90%. That gives a significant time saving. That gives simulation engineer more time to optimize their design, run more scenarios, go to market sooner, and whatever else can provide a better benefit. The second step is that we can then start looking at the model to check that design meets the required specifications. One particular task they need to perform often is sizing the system so that you're getting the correct flows, pressures, velocities, and the components in order to get the best possible design. Some questions you might need to answer include, what's the best pump or valve I can use in this piping system? What's the best heat exchanger that I can use to ensure efficiency, meet space requirements, anything else? Flowmaster for Solid Edge provides a fast and reliable static solver that allows you to perform this operation quickly and efficiently. Another task you quite often asked to cover is flow balancing the system. What we mean by flow balancing is, if I look at this example here, it may be that I want equal flow through each of these paths, or I want 20% of the flow to come from one direction, or even I want to achieve a total flow to this point here. So the way that we would typically do this is by either using control valves or calibrating orifice plates to ensure that you get the right flow through each branch of the system. SimCenter Flowmaster for Solid Edge, as supplied, comes with a best-in-class flow balancing capability to form this type of simulation. This isn't done by running an optimization, so you don't have to run many simulations. Basically, what you do is you will enter into the datasheet the flow that you want through a particular orifice or valve, and it will return directly what the size of the orifice plate should be or what the valve position should be, without having to do a parametric run that may take a bit of time. Finally, at the end of it, we have the result visualization. So this example is showing pressure, but we can draw pressure drops, velocities, flow rates, temperatures directly onto the schematic. We can also display all the other results we might want to see, and that enables us to quickly understand the system behavior at a single glance. And also, if we're trying to pass our results on to others, it's a lot easier to explain in that way. Third step is taking that same model that we've set up for static analysis. We can then move on and look at dynamic operations. So this might be shutting the system down, starting it up, and then making sure it performs as we want. So we can use the same model again and again for different scenarios, basically just by adding some control onto it. Some examples might be a tank filling and emptying scenario, warming up and cooling down the system, pressure surge where we either switch off the system rapidly or we have a pump failure. So and essentially one of the safety critical investigation engineer might be asked to perform is about pressure surge. In this context, engineers need to study the failure and emergency scenarios where an isolation valve needs to be suddenly closed or pump is tripped due to failure. These give a pressure surge event. So this is an example we're showing on this graph here where we're getting a high pressure here of around probably 13 bar there looking at that. And sometimes with those scenarios can cause failure in real systems. So with SimCenter FlowMaster, we can look at study all those dynamic scenarios. And with the visualization, because we can also plot the pressure flow transiently on the network as well as these static things here we're seeing, we can identify the critical areas and ensure safety. So we're just going to look at this with a quick video showing this sort of step by step as we go. Some sections have been sped up to save a bit of time. I'll walk you through it. So we start off in Solid Edge here, and I'll just start the video. So we go to the Fluid Export toolbar. We select the CAD to FlowMaster. We've already prepared the model here and put some lids on the fluid geometries. And we'll click the Create Fluid Volume button. This will identify the fluid volumes in blue there. We can see on the network, or sorry, on the assembly. And then we'll just pick a face, and based on that, we'll work out some approximate lengths and convert this to a subsystem. And by doing that, we'll get a series of components in these two panels here, which will come up with pipes, bends, elbows, any junctions. So you can see here the different elements it's identified. And we can see them here on the assembly with the points as well. So we just go through the points there in the control. And then we can export that to FlowMaster, and that will save a CAD to FM file that even if we want to come back afterwards, we could re-import again. But by default, it will open up inside FlowMaster. We will then be taken through, we'll see a 3D representation of our model that we can rotate around so that it matches the orientation that we want our network to be built up in FlowMaster. We've got some default data over here for the roughness and wave speed, and we'll move to using a 3D projection, same as we've got here, and just hit import. This will import it as a subsystem. All those pipes, bends, transition components will have data assigned to them. We're actually going to take out the sub-circuit that we want. We only want to look at one between the compressor and the vessel in this case. So I'll just export that and just save it to reuse it. We could do that for each of the subsystems here if we wanted. And then what I'll do is I will take that and I'll add that to a network. So I can see here, I've just checked I've got the subsystem I wanted to extract. I'll close it. And then I'll just add that to a network. Next thing I need to do is add my boundary conditions. I'm going to use a pressure source for this. So just drag it in, connect it onto the end of the circuit, and I'll specify a pressure of 1.04 bar. And I've copied that pressure source to connect to the other side and just connected it up at the top and set that back to 1 bar. Then I'll run a static simulation. I'm going to use air as my fluid. This is just a compressor circuit. And then following on from that, I've got my results and I can then start visualizing my flows. I'm getting a bit more from the left-hand side here. If I look at the pressure, I can see I've got higher pressure around its either end. And I can also go in. I'm now moving to a transient simulation, assigning a pressure wave curve. And then I'll have run my dynamic simulation with a time step. And then afterwards, I can see how the flow rate varies from into the tank. And finally, I can also run a dynamic simulation here, looking at how the pressure varies with time as we move between the two compressors and their oscillations. So that's a very, very quick overview of the workflow step by step. So just to go over that again, by going from the automated extraction from the CAD geometry to the efficient steady state sizing and balancing through to the dynamic operations with a single model, we can very quickly build a system and understand how it's going to behave. We're now going to take a look at some customer examples. The first one is from the Nian Polytechnic University, where they were looking at implementing a new pumping system. And to quote Dr. Sam Lee from the Nian Polytechnic, using 1D CF tools such as SimCenter FlowMaster is one of the fastest and most cost-effective methods to design piping systems. In this case, we used SimCenter Flowmaster to design the HVAC for a large building. Possibility to rapidly explore designs allowed him to find an optimal design that could achieve 55% energy savings in the new primary coil secondary pump system. So here, by using the static solver early, we managed to save a lot of energy by optimizing our design. The second example we're going to look at is a dynamic example from ConsiLab GmbH. And in this case, they were looking at what happened when they closed these valves here and looking at the pressure surge. So the accuracy of Flowmaster here allowed ConsiLab to rapidly evaluate alternatives to avoid unwanted pressure surge. This is a really good example here of the being able to use Flowmaster to design a system so it performs in a safe way while also being efficient. The final example we're going to show is from Eurotechnica, which again is a surge example looking at a solar farm here. And by using Flowmaster, they allowed them to study and define emergency maneuvers to guarantee the safety of the system. Again, used early in the work, and you could have taken that geometry straight from the CAD. So in summary, SimCenter Flowmaster for Solid Edge can be used to improve the flow of piping system design. Streamline workflow, quickly compute and visualize flow velocity, pressure, and temperature drop in piping systems starting from the 3D CAD geometry of Solid Edge. You don't require simulation expertise and allows engineers to quickly understand the behavior of the fluid system. And finally, that integrated streamlined workflow means that every design engineer can take advantage of the simulation and improve their productivity. And thank you for attending the webinar.
All right, thank you so much, Chris. And if you have an immediate project in mind and you're looking for some help, go ahead and give us a call. And this concludes today's webinar. Thank you so much for joining us, everyone, and have a great rest of your day.